Multiplication of a matrix by a scalar. As we dive into the study of matrices, you will find that we often encounter situations where we need to adjust or scale the entire set of data contained within a matrix by a specific factor, whether that means doubling all the values, halving them, or increasing them by a certain percentage. This specific mathematical operation is known as scalar multiplication. Hello, everyone. Today, we are going to begin our lesson on a fundamental operation in linear algebra. In the upcoming slides, we will define exactly what a scalar is and walk through the step-by-step process of how to apply it to a matrix. Understanding the concept. Now that we have introduced the general idea of scaling data in the previous slide, let us clarify some essential terminology before we dive into the actual mechanics of the operation. First, let us define what we mean by a scalar. In the context of linear algebra, a scalar is simply a real number. For instance, it could be a whole number like 5, a negative number like -2, or a decimal such as 0.5. It is referred to as a scalar because its primary function is to scale the magnitude of the elements it multiplies, either increasing or decreasing their value. Building on this, scalar multiplication is the process of multiplying every single individual element within a matrix by that constant scalar value. It is important to note a key distinction here. Unlike matrix addition, which requires two matrices of the same dimensions to be compatible, scalar multiplication does not require a second matrix. You only need one matrix and one scalar. Furthermore, this operation is universal. It can be performed on any matrix, regardless of its order or dimensions, whether the matrix is square or rectangular. Once you are comfortable with these basic terms, we will move on to the formal mathematical definition in the next slide. Formal definition. Suppose we have a matrix A, represented by elements a sub ij with an order of m by n, and we have a scalar, which we will call k when we calculate the product Ka. The resulting matrix will maintain the exact same dimensions as the original, meaning it will also be of order m by n. Each individual element in this new matrix is obtained by multiplying the corresponding element of matrix A by the scalar k. To express this mathematically, we say that K equals K times the matrix a sub ij of order m by n, which is equal to the matrix where every element is K times a sub ij, all while keeping the order m by n. In practical terms, this means that if you are looking for the value at the ith row and jth column of your resulting matrix, it will simply be the scalar k multiplied by the element located at the ith row and jth column of the original matrix, A. Now that we have established the terminology and the general concept of scalar multiplication, let us move on to the formal mathematical definition. With this formal definition in mind, we can now transition from the theory to the actual practice. In the next slide, I will walk you through the step-by-step process of how to perform these calculations. Step-by-step process. Now that we have established the formal definition, let us move on to the practical application. To multiply a matrix by a scalar, you can follow these 4 simple steps. First, identify the scalar. This simply means you need to determine the constant value, which we have been referring to as k, that you are required to multiply by. Second, distribute the scalar. This is a critical step. You must apply the scalar to every single individual element inside the matrix. It is important to ensure that no element is overlooked. Third, calculate the products. At this stage, you will perform the actual multiplication for each element using the scalar you identified in the first step. Finally, construct the resulting matrix. You will take these new calculated values and place them in their original positions to form the final matrix. Once you are comfortable with this process, we will apply these steps to a real-world scenario in the next slide to see how this works in practice. Real-world application example. Imagine a small business that sells 2 different products, product X and product Y, across 2 different cities, City A and City B to keep track of the pricing, the business stores the current prices in a matrix, which we will call matrix P. Matrix P is a 2x2 matrix. In this matrix, the rows represent the cities and the columns represent the products. The first row contains the prices for City A, which are 100 and 150. The second row contains the prices for City B, which are 120 and 180. Now, suppose that due to inflation, the business needs to increase all of its prices by 10%. In mathematical terms, increasing a value by 10% is the same as calculating 110% of that value. Therefore, we need to multiply our price matrix by a scalar of 1.1. Let us walk through the calculation step by step, applying the process we discussed in the previous slides. In step 1, we identify our scalar k, which is 1.1. In step 2, we set up the multiplication. We write this as 1.1 times matrix P. This means we are multiplying the scalar 1.1 by the matrix containing 100, 150, 120, and 180. In step 3, we distribute the scalar. As we learned, scalar multiplication is an element-wise operation, so we multiply every single entry by 1.1. This gives us a matrix where the elements are 1.1 times 100, 1.1 times 150, 1.1 times 120, and 1.1 times 180. Finally, in step 4, we perform the actual multiplication to find the final values. This results in a new matrix containing 110, 165, 132, and 198. This resulting matrix provides the business with the updated prices for all products in both cities, while maintaining the original structure of the data. Now that we have covered the formal definition and the general steps of scalar multiplication, let us look at how this concept is applied in a real-world scenario to better understand its utility. Now that we have seen a practical application with a positive decimal, let us move to the next slide to practice with a purely numerical example involving a negative scalar. Numerical example. Now that we have seen how scalar multiplication applies to a real-world scenario, let us work through a purely numerical example to solidify your understanding of the mechanics. Let us consider a matrix, which we will call matrix A with an order of 2 by 3, and a scalar, k, equal to -2. To visualize this, matrix A consists of 2 rows and 3 columns. The first row contains the elements 4, -1, and 0, while the second row contains 3, 5, and -2. Our objective is to find the resulting matrix when we multiply -2 by matrix A. Following the step-by-step process we established in the previous slides, our first step is to distribute the scalar to every individual element within the matrix. This means we multiply every single entry by -2. Mathematically, this looks like this. In the first row, we have -2 times 4, -2 times -1, and -2 times 0. In the second row, we have -2 times 3, -2 times 5, and -2 times -2. Now, let us move to the second step and perform the actual multiplication for each position. Starting with the first row, the first column is -2 times 4, which equals -8. The second column is -2 times -1, which gives us +2. The third column is -2 times 0, which is simply 0. Moving to the second row, the first column is -2 times 3, resulting in -6. The second column is -2 times 5, which equals -10. And the third column is -2 times -2, which gives us +4. Finally, in step 3, we construct the resulting matrix by placing these new values in their original positions. The final matrix, -2A, is a 2 by 3 matrix where the first row is -8, 2, and 0, and the second row is -6, -10, and 4. As you can see, the dimensions of the matrix have not changed, which is a key takeaway we will discuss in the next slide. Also, pay close attention to how the signs changed when multiplying negative numbers, as this is a common area where errors occur. Key takeaways. First, let's discuss order preservation. This means that the dimensions of your matrix remain exactly the same after the operation. To put it simply, if matrix A has m rows and n columns, then the resulting matrix, K times A, will also have m rows and n columns. The size of the matrix never changes during scalar multiplication. Secondly, we have universal application. Unlike matrix addition or matrix multiplication, which have strict requirements regarding the dimensions of the matrices involved, scalar multiplication is much more flexible. It can be applied to any matrix, regardless of whether it is a square matrix or a rectangular one. Finally, remember that this is an element-wise operation. As we saw in our previous calculations, the scalar does not just affect one part of the matrix. It interacts with every single entry individually. Every element must be multiplied by the scalar to achieve the correct result. Now that we have walked through the theoretical definitions and worked through some practical examples, let us summarize the key takeaways to ensure you have a solid grasp of the concept. Now that we have covered the essential rules, let's move on to the final slide, where we will discuss some common mistakes to avoid so that you can perform these calculations with complete accuracy. Common mistakes to avoid. Now that we have walked through the theory and a few practical examples, let us conclude this lesson by discussing some common pitfalls to ensure you avoid them in your assignments and exams. First, let's talk about partial multiplication. A very frequent error students make is multiplying only the first row or the first column by the scalar and leaving the rest of the matrix untouched. Please remember the rule we established in our step-by-step process. The scalar must be distributed to every single element within the matrix, without exception. Secondly, you must be extremely careful with sign errors. As we saw in our previous numerical example where we used a negative scalar, the signs can be tricky. Always remember your basic arithmetic rules. Multiplying a negative scalar by a negative element in the matrix will result in a positive value. For example, if you multiply -2 by -3, the result is +6. Finally, it is crucial that you do not confuse scalar multiplication with matrix multiplication. While they sound similar, they are fundamentally different. Scalar multiplication, which is what we have covered today, is the process of multiplying a matrix by a single real number. Matrix multiplication, on the other hand, involves multiplying one matrix by another matrix. The procedures and the rules for those two operations are entirely different, so be sure to keep them distinct as you move forward in your studies.